For lesson 5.4, we're going to be talking about a new type of story problem. These story problems are called optimization problems, which is basically a fancy word for minimizing or maximizing something. So you may have heard of problems like this in the past where they're like, I want to build a pasture for my sheep and I want to maximize the area of the pasture. What should the dimensions be? That's the kind of problem we're talking about, maximizing or minimizing something. Now, there is this procedure written out right here for you. The most important part of this procedure, the one I really want you to remember, is rewrite with only one variable on each side. That's something we're going to talk about a lot in this lesson. Then, next thing we're going to be talking about is how to find max and mins, which is something we've talked about in the past. If we want to find a maximum or a minimum, we would do a first derivative number line. And then if that number line goes from increasing to decreasing, that's a maximum. And if it goes from decreasing to increasing, that's a minimum. So that's the key here. That's why it says right here that we're going to end up taking a derivative and making a number line. Because that's how we're going to find a maximum or a minimum, just like we've talked about in the past. Now, an important thing to know about these kinds of problems is you need to really understand the concept behind the problem, because there are a lot of different kinds of optimization problems. So you can't just memorize the steps for all of them. You have to really understand the concept and apply logic to it. So that's something we're going to focus on in these examples. So let's start with this first example. A box with no lid is made from 48 centimeters squared of material. If the box must have a square base, find the dimensions that produce a maximum volume. So the whole point of this problem is we are trying to maximize volume. That's what we're trying to do. So let's go to this picture right here. First off, we know that it has a square base, so I'm just going to call both of these W, width and width, and we know they're the same because it's a square base. We don't know what the height is, so I'm just going to call it H. So if I want to do the volume of this box, it's going to be length times width times height, or W times height, which would be W squared height. So now let's go back to that one key critical thing that I told you to highlight right here in the procedures. Rewrite with only one variable on each side. So if I look at this equation, if I look at the left side, check, only one variable on that side. If I look at the right side, that has two variables, which means I cannot take the derivative or make a number line of this equation yet. I need to get the right-hand side into one variable only. So this is where this first sentence comes in. A box with no lid is to be made from 48 square centimeters of material. So if I think about this 48 square centimeters, I know that that is an area. And I know that because the centimeters are squared. That's two-dimensional. So we're talking about two dimensions, kind of like we're talking about wrapping paper. We want to wrap this box in wrapping paper except for the top. So if I wanted to do that, the area of this part of this material would be W times H. And I'm going to have two of those. That one is also going to be a W times H. Now if I look at this one, hey, look at that. That is also W times H. So now I've got three of them. And this one in the back is also going to be W times H. So I've got four W times H's right there. And then I need to add the area of this bottom piece right here, the square bottom. So the area of that bottom piece is going to be W times W, or W squared. And if I add all those sides together, that should give me how much material I make for the box. So now I've got another equation. Now let's go back to the concept. Remember, the whole point in this was we're trying to get this equation to one variable on each side, and we're trying to maximize this volume. Well, can I use this equation to get this equation to one variable? Absolutely. I can take this equation and solve for either one of these letters. I could solve for W or I could solve for H, either one, and then plug it into here. So like I said, you can do it either way, and you should end up with the same answer we do at the end. I'm going to solve for H. So really quickly, let's go through this equation. And I'm going to solve for H. Okay, there we go. And then I'm going to plug that H equation in for H. So now let's go back to our main thing. Rewrite with only one variable on each side. On the left-hand side, I have only V's. On the right-hand side, I have only W's. Check. So now that I have it with only one variable on each side, I can take the derivative. But if I look at this right here, that derivative is going to be pretty gross. So let's do some simplifying first to make the derivative simpler. So what I'm going to do is, I know this is a W squared and a W, so I can cancel one W on top and one on bottom. So then I'm left with this. Then I can distribute that W in. So I get 48W minus, oh, oops, that should be W squared, isn't it? I was thinking something was wrong. And minus W squared. There we go. Minus W cubed. Ta-da! Much better. Okay, and last, I'm going to divide both of these by 4. So 48 divided by 4 is 12. And this one I'm just going to write as a 1/4. And now I can see this derivative is going to be way easier to take than that derivative. So now let's take my derivative and look at the number line. So here's my derivative. So derivative of V is going to be V prime. Derivative of 12W is going to be 12. And then derivative of this should be negative 3/4 W squared. Take the 3 in front, minus 1. So here's my first derivative. I am looking for, once again, let's remind ourselves, a maximum. So if I think on a number line, a maximum should go from increasing, which is going to be positive, to decreasing, which is going to be negative. So this is what I need to see on my number line. But first I have to make a number line. So we remember, what goes on a number line? Critical numbers. And critical numbers are where your equation either equals 0 or it equals undefined. Well, this equation isn't ever going to be undefined, so we don't really need to worry about that one as much. So I'm going to set it equal to 0 and solve it. I got this. So square root of 16 is plus or minus 4. But remember, this is width on a box. Negative 4 centimeters doesn't really make sense. So I'm not going to think about the negative. So I'm just going to think about the positive 4. And I'm actually going to put this 0 here, because I know that I can't have negative dimensions. That's just weird. So here's our number line. Let's plug numbers in and see what we can get. So let's plug in 2. So I'm going to have 12 minus 3/4 2 squared. So 2 squared is 4. So that would be 12 minus 3, so that's a positive. And let's do 5. So 5 squared is 25, so that's 12 minus 75/4. That's a negative. So we got an increasing to a decreasing, so voila! We have just proved that 4 is indeed a maximum. Now, word of warning really quickly. This is a very common AP test trick. Is a lot of students will get to this 4 and assume that's our answer and just go with it. But it may be that when you make your number line, this 4 is actually a minimum, not a maximum. So then your answer would then be, there is no maximum volume, it doesn't work. And that's a very common AP trick because a lot of students will forget to check this last step. So be careful to always make a number line and check to make sure that you're actually getting the maximum you want. So here we go. We know that the width should be 4. And now I can also find the height using this equation. So 48 minus 4 squared all over 4 times 4, which is going to be 2. So the dimensions that will produce a maximum volume, let's write this out in sentence form. The dimensions that produce a maximum volume are when the width is 4 centimeters and the height 2 centimeters. Something like that. Doesn't have to be exactly that. And there we go. That is your first optimization problem. In the next video, we'll do the second problem.